This is the final 5.3 video. We're going to look at when to use the multiplication rule for independent events to compute probabilities. So we've learned the general multiplication rule. That works for any type of events, independent or not independent. But this rule specifically only applies to independent events. And that is if A and B are independent, then you can just multiply their probabilities together to calculate the probability of A and B occurring. So let's look at three examples here. Following the Space Shuttle Challenger disaster, it was determined that the failure of O-ring joints in the shuttle's booster rocket was to blame. Under cold conditions, it was estimated that the probability that an individual O-ring joint would function properly was 0.977. So assuming O-ring joints succeed or fail independently, what's the probability all six would function properly? So they tell us that they succeed and fail independently. So they're independent events, whether they succeed or fail. So we're just going to multiply if all six function properly. So if one function properly, so it's 0.977. So we're going to multiply this times itself for each O-ring joint. So first I've identified that S represents an O-ring joint succeeding. So I'm trying to find the probability of a success and a success and a success 6 times because there are 6 total. So all I have to do is multiply the probability of one success times the next. So 0.977 times 0.977 repeated for all 6. So it's going to be 0.977 to the 6th power, which is approximately 0.8697. So we can multiply these together because they are independent events. The success of the first one doesn't influence the success of the second one. That's what independence means. First event doesn't influence or change the probability of the next one. Let's think about a different question here now. What if they wanted to find out what's the probability that exactly one fails? So the thing to think about with this problem is exactly one could fail in a number of different ways. It could be the first one to fail, or it could be the second one, or the third, or the fourth, or the fifth. So it's going to be the probability of the first one failing, or the probability of the second, or the probability of the third, or all the way until the sixth. So I'm going to have to add all of those probabilities together to find if exactly one fails. Okay, so I didn't write these in probability notation just because of the amount of space that I had. But this is all the different options that satisfy exactly one failing. Could be the first one fails, the next 5 are successful. Could be the second one fails, and the remaining 4 and the first were successes. So all of these are all possible options for how exactly one fails. So the question is, what's the probability of this first one happening? What's the probability that the first one fails and the next 5 succeed? Since they're independent, we can multiply the probability of each of these together. So if the probability of a success is 0.977, then the probability of a failure is going to be 1 minus that. So 1 minus 0.977 is going to be 0.023. So this probability is going to be 0.023 times 0.977 times 0.977 times 0.977 for each of these successes. So you can see the probability of one failing is the complement of it succeeding because it will either fail or succeed. So 0.023 added to 0.977 should equal 1. So this is the probability of the first one occurring. What's the probability of the next one? We're going to add. This time it's going to be 0.977 times 0.023 times 0.977, 0.97, multiply them together. This actually is the same probability as this first one because there is one failure times 5 successes. There is one failure times 5 successes. The order is just a little different. Think about this one. This is going to be, again, 5 successes, 1 failure. All of them have 5 successes and 1 failure. So really, I'm going to add this to itself 6 times because each of these have the same probability of occurring. So instead of adding them all up, I'm just going to multiply by 6 because that's the same thing as adding them together 6 times. So if I add this together 6 times, I should get a probability of 0.1228. So there is about a 12.3% chance that exactly one fails. Now it is important that you understand I'm saying exactly one because if I said what's the probability that one fails, well, that's a different question because that could be, I mean, if 3 of them fail, then technically one has failed. That's what we're going to talk about in the next question here. So this is exactly one. The probability of at least one is a different problem here. So let's look at a different example. Many people who come to clinics to be tested for HIV, the virus that causes AIDS, don't come back to learn the results. Clinics now use rapid HIV tests that give a result while the client waits. In a clinic in Malawi, for example, use of rapid tests increased the percent of clients who learn their test results from 69% to 99.7%. The trade-off for fast results is that the rapid tests are less accurate than slower laboratory tests. Applied to people who have no HIV antibodies, one rapid test has a probability of about 0.004 of producing a false positive. That is, of falsely indicating that antibodies are present. So if a clinic tests 200 randomly selected people who are free from HIV antibodies, what's the chance that at least one false positive will occur? So now we're looking at a chance process that's repeated 200 times. And they want to know what's the probability that at least one occur. So the first thing you need to be aware of is that whenever we see the words at least one, that is a symbol for you to use the complement rule. It should, every time you read at least one, you should think, I know I need to use the complement rule. And the complement rule is the probability of not A equals 1 minus the probability of A. So we're going to use this rule for this problem. But first, let's think about all the outcomes from this example. So they want to know what's the probability that at least one false positive will occur in 200 randomly selected people. So think about how many different ways a false positive could occur. It could be the first, and then there's 199. It could be the first and the second, and then there's 199. Or it could be the first, second, and third. It could be the first, second, and fourth. Or it could just be not the first and the second. There are so many different options that satisfy at least one out of 200 people. I'm just going to start to write out a couple of them to give you a visual of what I'm talking about. Okay, so thinking about this 200 people, the probability of a false positive is 0.004. That means the complement is going to be the probability of them getting a negative result, which is the test working correctly. And so for this problem, the only way you can get a false positive is if all of these 200 people don't actually have HIV. The only way you can give a false positive is if the person does not have HIV. So using the complement rule, if the probability of a false positive is 0.004, then the probability of them getting the negative result, the correct result, if they don't have HIV, is 0.996. So thinking about these 200 people, this statement here is showing the first person is the person who gets the false positive, and the remaining 199 do not. This is the second person, continued for the rest. This is the third. And there are so many different options just for exactly one, but we're not asking about exactly one. We're asking about at least one, which means it could be two. So it could be the first two or the second and third. And we can continue this until, think about, all people get a false positive. That could satisfy at least one getting a false positive. So what we'd have to do if we don't use the complement rule is we would have to write out all of these options and we'd have to add all of them together, which would take forever. So instead, let's find the probability that no one gets it. So I've defined my events as I've just called A is that there are no false positives in all of the 200 people. The complement would be at least one because this A or not A is guaranteed to happen. You're either going to have no false positives or you're going to have at least one false positive. And so we can calculate the probability that there are no false positives much easier than calculating the probability that there's at least one false positive because we can just use this complement rule here. So how can we calculate the probability that there are no false positives? If there are 200 people and the probability of a false positive is 0.004, we're going to multiply 0.04 times itself for each person. And so the probability of at least one positive, false positive in the 200 people is going to be 0.5514. So remember, if you see at least one, it's your cue for using the complement rule. Identify your events, A as no false positives or whatever it is for your scenario, and the complement would be at least one, and apply this rule to answer any at least one probability question.